Hi. In today's video we want to use the ideal gas law to solve 5 simple problems. These examples will help you, I hope, and help you learn how to use the ideal gas law. So last time we talked, we used this equation here, and we said this was the ideal gas law. And so I'm going to show you how to use this equation toward solving various kinds of problems. And this is very important down here. I recommend that you pause the video at various points when the problems are revealed and try them. Try to solve them yourself, and then you'll see me work through them, and this will give you feedback on what you're doing and might be able to help you. Alright, in this first example we're told that we have 65 grams of nitrogen gas, and we're sealed inside of a 2-liter container. We're going to heat that gas to 100 degrees Celsius, and I want to find the pressure inside the container. So, what are we solving for? We're solving for the pressure, and we're given various information here to help us do that. The first thing we're going to need, and this is a starting place many times we talk about gases, is the ideal gas law equation. PV is equal to nRT. I'm also going to need to recall what the gas constant is. And so recall from last time that R is equal to 0.08206 liters atmospheres per mole Kelvin. Alright. Now the reason that R is so important is, well, remember, it's our proportionality constant. And we have to make sure that the input into our equation, before we just start plugging values in here, we have to make sure that the input into the ideal gas law equation matches the units on R. So we have to make sure that our volume is in liters, our pressure is in atmospheres, and moles in Kelvin, etc., etc. And so here we're given the amount of gas that enters the tank, but we're given this in terms of grams and not moles. So the first thing that we need to do now is do a simple grams to mole conversion. So remember that nitrogen is diatomic. That means that 65.0 grams, we're going to say that they are 28.02 grams of N2 in 1 mole of N2. And when we work this out, we find that there are 2.319 moles, and we'll underline this 1 here as our last sig fig. We're also given the temperature in terms of Celsius and not Kelvin, and so we have to add 273.15 to this 100 degrees Celsius, and when we do that we find that we have 373 the 0.15 rounds to 0.2 Kelvin. So now that we have our volume is already in liters, our amount of gas is in moles, and our pressure is in Kelvin, we're ready to start using the ideal gas law. And so we take the starting place of ideal gas law, PV is equal to nRT, and we're solving for the pressure, so we want to rearrange the equation, and we'll say that the pressure is equal to nRT over the volume, and then we have to just simply plug in all the things that we used. We said that the moles was 2.319 moles, and if you're really careful with your units here, there's no reason to worry. The volume was 2 liters, 2.00 liters. The temperature is 373.2 Kelvin. And the last thing that I have to use is R, and I have to put the gas constant in here. I'm going to change the gas constant to red just so you can see how I'm doing this. 0.08206 liters atmospheres, and then in the denominator moles Kelvin. I recommend students avoid compound fractions if they can, and in this way you'll see that the units cancel nicely for us. The moles here cancels with the moles here, the Kelvin here cancels here, The liters cancels the liters, and that tells us that our answer is going to be in atmospheres. Is that what we want? Yes, that's a great unit of pressure to use. And if we solve all this out and we round to 3 sig figs, now it's just time to use the calculator. We find that the answer is 35.5 atmospheres. Let's try our next example. In this case, we're told that carbon dioxide is added to a 50-liter tank until the pressure reaches 6 atmospheres. And this is done at room temperature. And we're asked to find how many moles are present. So once again, we're going to start with the ideal gas law. And we're going to rearrange the variables till we're isolating the one that we're solving for. So in this case, we start with PV equals nRT. But we were asked to solve for the moles, so we're going to rearrange this equation and we're going to isolate the N here. And so we're going to find that N is equal to PV over RT. And once again, we have to remember to change our unit of temperature to Kelvin. We always want to use Kelvin when we're using the gas laws. And then it's simply a matter of just plugging everything in here until we get it right. So let's switch over to the next blank screen here, and we'll say, okay, N is equal to PV over RT. Alright, so we simply plug everything in here. We have our pressure is equal to 6.00 atmospheres. Our volume was 50.0 liters. R, once again I'm going to put in red, 0.08206 liters atmospheres. Moles Kelvin's going to go in the numerator now. And the temperature is 298 Kelvin once we change the 25 Celsius to Kelvin. Here the units cancel where they should. The unit of atmospheres here cancels with atmospheres here. The unit of liters here and here cancel. And Kelvin cancels with Kelvin. And my final unit is moles, and that's exactly what I'm expecting given that I was asked to solve for the number of moles present. And when we just plug everything in and we use the calculator, make sure our parentheses are in the right place, we get 12.3 moles. And this is moles of CO2. Now, was the fact that it was CO2, was that material to the problem? No. The ideal gas law, one thing to recognize is that it treats all the gases the same. We just simply plug in the number of moles of gas, and we don't care if it's hydrogen or helium or CO2 or any other kind of gas. It treats all the gases the same. Alright, let's try our next example. In this case, we're told that we have 50 grams of an unknown noble gas. It occupies a volume of 28.1 liters at STP, and we're asked to identify the gas. Before we do that, now would be a good time to tell you what this abbreviation here, STP, refers to. STP is what we call standard temperature and pressure, and it's simply a reference point, standard conditions, and it's defined as 273.15 Kelvin, that's 0 Celsius, and 1 atmosphere of pressure. This is nice if you have a given set of conditions that you can compare one system to another. It's nice to have a reference point, and this is nothing more than that, standard temperature and pressure. So we're asked to find this gas, and we're told we have 50 grams of the gas and occupies this this volume, and we're also told the temperature and pressure. And so in this case, if we want to identify the gas, it'd be a good idea to identify the molar mass of the gas. We know it's a noble gas, so we know it's going to be a group 18 gas. If we can find its molar mass, the grams per mole, we should be able to identify it by its atomic weight. And the good news is that we are already given the number of grams it has. So in a weird kind of maybe camouflaged way, what this question is really asking us to do first is to find the moles. If we can find the moles of gas, we can identify the molar mass. And so once again, here we go, application of the ideal gas law. PV is equal to nRT, okay, or N, and we used this equation I think on the last problem. N is equal to PV over RT, and we simply go from there. Alright, so N is equal to, what's my pressure? My pressure, remember it was standard temperature and pressure, so the pressure is 1 atmosphere pressure, and the temperature is 273.15. Put that in the bottom where it goes, Kelvin, and the volume was 28.1 liters. And now I need to put R in, 0.08206 liters atmospheres mole Kelvin. And the reason I keep putting that as red is my experience that students don't like or aren't accustomed to dealing with that. So I'm just trying to help you out. When we solve for this, we once again see that the units cancel. Atmospheres cancels with atmospheres, liters with liters, Kelvin with Kelvin, and we're left with moles. And when we get our calculator out, we find that this is 1.2536 moles. And now we remember that we had 50 grams of the gas, so 50.00 grams per 1.2536 moles. We find that this is 39.9 grams per mole, and so we know the gas must be argon. Alright, pretty neat, right? Let's move on to our next example. Just two more examples left. Thanks for hanging in there. And in this example, we're asked to find how much volume would be occupied by 1 mole of gas at STP. So once again, we're at standard temperature pressure, and we want to find the volume occupied by 1 mole of gas. So if we start with PV equals nRT, all right, we want to solve for the volume, so we'll say that volume is equal to nRT over P. And now we simply plug everything in again. So we were told that we had 1 mole of gas. Remember, we're going to do nRT over P, right? So we have 1.00 moles of gas, and R, once again, 0.08206 liters atmospheres moles Kelvin. Alright, and we were at 273.15 Kelvin. Okay, you will need to learn standard temperature pressure so that when people say that, you know what they're talking about. And then the standard pressure was 1 atmosphere. And plugging everything in here, we find that the volume is 22.4 liters. Alright. The reason that we did this problem is that this 22.4 liters per 1 mole is kind of a handy kind of relationship. So if we kind of remember this, this will help us be able to make estimates in the future. So what we just learned is that 22.4 liters equals 1 mole of gas at STP. So this will just kind of be something to remember for the future use. Let's move on to our last example, and in this case this is a gas that we're told 25 grams of an unknown gas sealed inside of a 20-liter steel container, an initial pressure of 1 atmosphere, and a temperature of 350.0 Kelvin. And let's see this right now. This is going to be, let's say this is exactly 1 atmosphere. And what we're asked to find is the temperature the gas must be heated to cause the pressure to rise to 1.25 atmospheres. The way to approach this problem is to think about the fact that you have kind of two conditions. You have the conditions before the heating and you have the conditions after, or when the heating's completed. But remember that the ideal gas law applies in each of these cases. So what we say here is, okay, P1 V1 is equal to N1 RT1, right? And over here we'll say, okay, P2 V2 is equal to N2 RT2. Notice I didn't put an R1 and R2 because the gas constant is a gas constant, and it's constant regardless of what temperature or pressure conditions that we're at. And the reason that we bring this up is to show you that we can use the ideal gas law in much the same way that we used Charles' law, Boyle's law, and Avogadro's law in the last lecture. And that is to say that if we go ahead here and isolate R and solve for it in each of the two cases, what we find is that P1 V1 over N1 T1 is equal to R, and over here you have the same thing except for all the 1s are 2s now. P2 V2 over N2 T2, and this equals R. Well, if two things are equal to R, then they're equal to each other, right? So what we can say here very neatly is that P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. Now we should be able to derive this relationship anytime that we want to. And the cool thing is that in this case we are given a situation where this 20-liter steel container, presumably the volume stays rigid or fixed, and so that V1 is equal to V2, and if V1 equals to V2, then these guys cancel off. And if the container doesn't leak, the same 25-gram sample that's available at the beginning of the problem is also available at the end of the problem, and N1 cancels with N2. In other words, N1 equals N2. And so we're able to take this relationship that we just found and rearrange it to suit our needs. So P1 over T1 is equal to P2 over T2. And now we're asked to find the temperature, the new temperature that we must heat the gas to. So we're going to rearrange this, and we're going to try to solve this simple equation for T2. And so we just simply do a little bit of cross multiplying here, and what you find, if we move, I'll just go ahead and move to the next slide so I have some room here. I find that T2 is equal to T1 times P2 over P1. Alright, so the original pressure we were at, P1, is nothing but 1 atmosphere, or what we said, exactly 1 atmosphere. And the original temperature is 350 Kelvin. And we were going to heat the gas until it reached P2 of 1.25 atmospheres. Alright, and so once again atmospheres cancels with atmospheres, and when we solve the problem, we find that T2, or the new temperature, the temperature to which we must heat the gas, is equal to 438 Kelvin. Okay, So again, the reason that I picked this example was just it shows the utility of the gas law towards rearranging it and solving problems that are very similar to Boyle's law, Charles' law, and Avogadro's law. And in fact, remember that we used those laws to derive the ideal gas law, and what we've shown is that you can use the ideal gas law and now go back to those original laws should you need to. So in conclusion, we've done 5 simple examples using the gas laws. Hope you're able to take something out of each one. And we defined standard temperature and pressure as 1 atmosphere pressure and 273.15 Kelvin. Remember, that's 0 Celsius. And then we also found the molar volume of an ideal gas at standard temperature and pressure to be 22.41 liters. Alright, so thanks for watching. You need to try lots of examples with the ideal gas law. It's not hard at all, but you have to try lots of examples and get the hang of it. And if you have any questions, you can always feel free to email me or stop by the office. Alright, thanks.